Hi, and welcome to this video about a control co-design optimization framework with mixed fidelity fluid and structural analysis. My name is Dennis Gabriel Capras. I'm a postdoc at Brigham Young University, and as part of this project, my presentation focuses on the aerodynamics modeling tools. The aim of our research is to develop a computationally efficient optimization framework for design of floating offshore wind turbines. Our specific aim is to utilize high-fidelity aerostructural tools and to derive reduced-order models directly from these high-fidelity tools. Our project is executed by a multidisciplinary team consisting of Rutgers University, University of Michigan, Brigham Young University, and NREL as primary partners. We are also collaborating with the National Technical University of Norway and the Technical University of Denmark. For a long time, wind turbine design has relied on engineering expertise, best practices, and low-fidelity tools. What's more, design practices often consider all the disciplines separately or one at a time, which tends to downplay the potential interactions that can exist between them. For new concepts such as floating systems with very long flexible blades, there is an opportunity to come up with improved designs that could take advantage of such tight connections. So the general idea in this project is that we want to consider all the relevant disciplines in a monolithic approach, meaning that, for instance, we solve simultaneously for the aerodynamics, the structures, the hydrodynamics, and the controls, potentially to obtain a more optimal design. The underlying objective is also to demonstrate the added value of using high-fidelity simulations within the design loop of a floating turbine. Now, high fidelity for us means computational fluid dynamics, which allows us to work with a fine description of the blade geometry. The optimal design itself is then obtained by employing gradient-based optimization, since this technique is more efficient to solve optimization problems with a large number of design variables. In this presentation, I will briefly summarize the modeling tools that we use for the aerodynamics in this project. I will then quickly review the novel approach that we developed in order to combine tools of different fidelities into a single rotor design optimization. That will lead me to some conclusions and future work. We work with different levels of modeling for the aerodynamics. The first level is a standard blade element momentum theory. We exploit the one-equation residual formulation of the BEM equations with guaranteed convergence, and for this project, we further developed the ability to perform gradient-based optimization using this tool. This led to a journal publication, and our code is open source and available on GitHub under the name ccblade.jl. The coupling of ccblade to a structural beam code for gradient-based optimization is also in progress. The second level we exploit is a RANS CFD solver that is capable of providing high-fidelity simulations of the rotor blade and aerodynamics. The solver we use is ADFlow, a code that is being developed at University of Michigan with a special focus on gradient-based optimization of aerospace applications. The method uses freeform deformation to control the blade outer shape. This way, we are able to optimize not only the blade twist and chord, but also locally the airfoil shape, which is a great advantage over conventional design techniques. Exact gradients are obtained through a dedicated adjoint. This is another great advantage as it makes the computational cost independent of the number of variables. In this project, ADFlow is coupled to a finite element code for the structures in a software framework called MAC. Please refer to the aerostructures and optimization presentation of this booth to learn more about this coupling and the related results. The third level of fidelity is provided through turbine foam. It is a RANS CFD method as well, but there the rotor blades are modeled with an actuator line model. We use it mainly to perform design analysis in this project. Finally, the various levels of modeling presented here are combined in an optimization framework, which I will talk more about in just a second. But the main purpose is to leverage the benefits of every level into a single rotor optimization, hence the name Combined Fidelity Approach. In this approach, we combine OpenFast and MAC that contains our high-fidelity aerostructural tools. Because it is already quite computationally intensive, our high-fidelity simulations are limited to steady-state conditions. This provides an accurate description of how the power production is distributed across the rotor. However, when designing a wind turbine, many unsteady load cases also need to be evaluated. That is mainly to guarantee the integrity of the structures in events including various turbulent winds, gusts, etc. The approach that we present here provides a way to combine steady high-fidelity simulations and unsteady conventional simulations into a single optimization. The result is a design that is both optimal from the perspective of the high-fidelity aerostructural solver, but also complies with the design load cases defined in the standards. Without going into details, the algorithm we designed works in two stages. In the first stage, in green, we perform many OpenFast simulations to determine the extreme loads and the fatigue loads on the turbine for a given design. In the second stage, in red, we keep the extreme and fatigue loads constant and we optimize the turbine design. This procedure is repeated until convergence, which we generally observed after 2 or 3 iterations. Finally, this algorithm also integrates well with control co-design, since we can re-optimize the turbine controller as desired during the first stage. In conclusion, in this project, we showed that using high-fidelity computational tools for the optimization of wind turbines offers a robust and automated way to explore their large design space. Additionally, high-fidelity optimization may also lead to optimal solutions that better exploit interactions between the engineering disciplines involved. It's quite obvious that having to run CFD within the optimization loop leads to significant computational expenses. However, we experienced that the added cost can be mitigated through the use of the combined fidelity approach. Indeed, it takes advantage of conventional tools to compute unsteady DLCs and high-fidelity tools to characterize the aerostructural details of the average power production. In the end, the computational power can be distributed so that the time to solutions only moderately increases with respect to conventional optimization techniques. Finally, the final product of this research is an open source computational framework that integrates all the capabilities developed in this project. On that note, I invite you to take a look at the other presentations of this booth, where you will discover more about our high-fidelity structural tools, the optimization framework, and the controllers that we developed. Future work regarding control co-design of floating offshore turbines is also discussed. Before closing, we would like to thank Professor Mario Garcia Sanz for the opportunity to participate in the Atlantis program. Special thanks to Dr. Dylan Temple, Dr. Carlos Noyes, Madeleine de Freitas, Michael Olsen, and the entire Atlantis team for their support. For questions related to this presentation, please use the contact shown. For questions related to the overall project and our tech-to-market activities, please contact the PI at the address shown. Here are some additional references. Thank you for watching this video.